Could you see my slide?
Yes, yes.
Okay.
So the title is Proof-Theoretic Analysis of Meaning of a Formula in a Combination of Intuitionistic and Classical Propositional Logic. So please start.
Yeah. My name is Masanobu, and coming from Hokkaido. And this is a joint. This work is based on discussion with Katsuhiko, who is a supervisor of myself. I'm really glad to have an opportunity to talk in this conference. First, I explain the themes of this talk. There are 3 themes. The first one is a proof-theoretic analysis of meaning of a formula based on the idea provided by Greg Restow. And the second theme is a combination of intuitionistic and classical propositional logic. And there are various ways to combine intuitionistic and classical logic, but I follow this red one in this presentation. And finally, assertion denial leading of a sequent and unilateralism bilateralism debate. And next, I proceed to the contribution of this talk. There are 3 contributions. The first one is the proof-theoretic analysis of meaning of a formula proposed by Restow is improved by making use of the method provided by Takano. And secondly, the analysis improved by Takano's method is applicable not only to pure intuitionistic and classical propositional logic, but also to a combination C+J. And finally, a proof-theoretic analysis of meaning of a formula in C+J can be obtained independent from the choice between unilateralism and bilateralism. And there are a table of contents, and it consists of 3 parts. First, I explain the Restow's analysis and introduce the sequent calculus for C+J. And secondly, I apply Takano's method to this sequent calculus. And finally, I talk a little bit about how these analyses related to unilateralism, bilateralism debate. So let's proceed to the first part. And in this section, I follow this Restow's paper. Before jumping into the detailed analysis, I explain the intuition of the Restow's idea. First, he refuses to introduce the notion of a model as given, and he tried to obtain the notion of a model from inference rules in the sequent calculus. And he regards inference rules in the sequent calculus as normative constraints on assertion and denial. And also, Restow applied his analysis to classical logic, intuitionistic logic, and modal logic S5 in the propositional level. Only the case of classical logic is explained here. In this analysis, the sequent calculus LK is used. And the sequent calculus LK consists of these actions and rules. And these are the actions. And these are the rules called structural rules. And these are the rules for connectives, right and left rules. And connectives are conjunction, disjunction, negation here. So let's proceed to the Restow's analysis. First, he starts his analysis by defining the notion of a position. And the position is defined as this. A pair of sets of formulas is a position if this sequence is not derivable in the sequent calculus LK. And in the following, I abbreviate this expression as this one for any sets gamma delta and for any formula AB. And this is just a formal definition, and I explain the intuition behind this definition. First, the antecedents and succedents in the position represent asserted and denied formulas respectively, and the position expresses a consistent linguistic act. So let's see example. P or Q is not the position. This is because P implies P or Q is derivable in the sequent calculus. And this fact represents to assert P and to deny P or Q is inconsistent. However, P implies P and Q. This one is a position, and this represents the fact that to assert P and to deny P and Q is consistent. And accordingly, the derivability of sequent represents the following situation. It is inconsistent to assert all the formulas in gamma and to deny all the formulas in delta. And an inference rule in LK is regarded as a normative constraint on assertion and denial. So let's see the example. Consider the rule cut formulated as this. And this rule is regarded as normative constraint described as follows. we lead cut from lower sequence to upper sequence here. So if to assert all the formulas in gamma and to deny all the formulas in delta is consistent, then either assertion of A or denial of A is also consistent. So this is a normative constraint cut represents. And based on the notion of the position, he defines the notion of limit position. A pair of sets of formulas is a limit position if it satisfies both of the conditions. The first condition is if we take the subset of each, the obtained pair is a position. And the second one is the union of gamma delta contains all formulas in classical logic. And technically, the notion of limit position corresponds to the notion of maximal consistent set in the proof of semantic completeness. And the intuition behind this limit position is the limit position is an ideal linguistic situation because all formulas are either asserted or denied in limit position. And about this limit position, we can get the following fact. For any position, there is a limit position which satisfies these conditions. And this fact is shown by appealing to cut, and which ensures the following for any A. If gamma delta is a position, then either this or this is also a position. And this is obtained by leading the rule cut from lower sequence to upper sequence. And we can get the following fact. For any limit position, both of the following hold. I limit the argument conjunction here, and the first condition represents the truth conditions for conjunctive formula. So A and B in gamma, if and only if both A and B in gamma. And the second part represents the false conditions for conjunctive formula. So A and B in delta, if either A in delta or B in delta. And the corresponding fact also for disjunction, negation, and false sum. And the formula which is an element of gamma can be regarded as true, and the formula which is an element of delta can be regarded as false. So starting from the admissibility of the inference rule, we can get the notion of truth and false, and we can get the truth condition and the false condition. So this is what Lestol had done. However, there are 2 points of improvement and one open problem related to Lestol analysis exists. So let's see the first point. In his analysis, the satisfaction relation for a complex formula is obtained from the admissibility of a corresponding inference rule. So in other words, Lestol's analysis explained the following. If an inference rule is admissible in a sequent calculus, then the corresponding satisfaction relation for a complex formula is obtained. However, if it is possible to establish the other direction, namely, if satisfaction relation for a complex formula is accepted, then some inference rule is admissible in a sequent calculus or something. A tighter relation between an inference rule and the corresponding satisfaction relation can be established. And let's proceed to the second point of improvement. Lestol's analysis depends on cut, the inference rule formulated as this. And recall that this rule is regarded as the following normative constraint. If to assert all the formulas in gamma and to deny all the formulas in delta is consistent, then either assertion of A or denial of A is also consistent. However, some may refuse to accept this normative constraint. What I have in mind is some intuitionistic logicians, because this normative constraint is very similar to the principle of bivalence. So some may refuse to accept this normative constraint. And moreover, if a semantic condition corresponding to the admissibility of cut is identified, this rule will not have to be treated as given, and we'll be able to treat it as loose for connectives. And there is an open problem for Lestol analysis. His analysis is applicable to both classical and intuitionistic propositional logic, which was already noted in this paper. However, this does not imply Lestol's analysis is applicable to a combination of classical and intuitionistic propositional logic. And the first and second points of improvement of his analysis are overcome by employing the method provided by Takano. And this method is applied to a combination of intuitionistic and classical propositional logic. And this ensures the open problem is solved positively. And finally, note that Takano's method is applicable to both pure intuitionistic and classical propositional logic. So before going into Takano's method, I explain a little bit about C++. First, the syntax consists of these two: a countably infinite set of propositional variables and logical connectives, for-some conjunction disjunction, and the intuitionistic implication and classical negation. And intuitionistic negation and classical implication can be defined. There are two implications and two negations in this syntax. And the Kripke semantics for this logic is obtained by adding intuitionistic Kripke semantics, the following satisfaction relation for classical negation, this one. So this is a very usual way of defining the satisfaction relation for classical negation. And I explain the sequent calculus, GC plus J. The sequent calculus for this combination is obtained by adding the right and left rules for intuitionistic implication into classical sequent calculus, LK. So this is sequent calculus, LK. And on the top of that, I add two rules for intuitionistic implication formulated as this. And this is the left rule, and left rule is the same as that of the ordinary multi-succeedent intuitionistic sequent calculus, but the right rule should be restricted as this form. And this sequent calculus was proposed in this paper, and this calculus is sound and complete to the Kripke semantics provided in these papers. And the sequent calculus is cut-free and satisfies the subformula property. And this property guarantees C plus J is a conservative extension of both intuitionistic and classical propositional logic. So let's proceed to the Takano's method, the main part of this presentation. In this section, I follow this paper mainly. First, I give the stipulation of the sequent calculus. The sequent calculus is a calculus having A implies A as an action for any A and having weakening and contraction rules. And by this stipulation, a sequent calculus containing only some rules in GC plus J can be discussed. And it is noted that the existence of cut is not assumed here. In the following, let GL be a sequent calculus. And we give some definitions related to subformulas. First, let A be any formula. Then sub A is the set of all subformulas of A. And for any set gamma of formulas, sub gamma denotes the set of all subformulas of some formulas in gamma. And next, we define notion of subformula closed. A set gamma of formulas is subformula closed, in short, SF closed, if these two conditions are satisfied. And in the following, if the side condition, this side condition, is imposed on cut, this restricted rule is denoted by cut A, and A is represents analytic. So cut A is analytic cut rule. And in the following, SF cross finite set Gusai of formulas is considered, while it is not considered in Takano's original paper. However, such a set is considered in these papers, and the finite model will be obtained by considering it. And relative to Gusai, we define the notion of derivability and admissibility. First, derivability. Let Gusai be a SF cross finite set of formulas, and the union of gamma and delta is subset of Gusai. Then a sequent is Gusai derivable in GL if it has a derivation in GL consisting solely of formulas in Gusai. And next, admissibility. The inference rule is Gusai admissible in GL if whenever all of the upper sequence are Gusai derivable in GL, then the lower sequence is also Gusai derivable in GL. And in the following, when it is said that a sequent is Gusai derivable or Gusai underivable, it is presupposed that this condition holds. And the notion of Gusai underivable pair of sets of formulas corresponds to the notion of a position in Lestow's analysis. And instead of the notion of the limit position, the notion of a Gusai analytically saturated pair is introduced here. And this notion is obtained by modifying the notion of an analytically saturated sequent, which was already introduced by Takano's paper. And this is a very important definition, Gusai analytically saturated pair. Let Gusai be a SF closed finite set of formulas. A pair of finite sets of formulas is Gusai analytically saturated in a sequent calculus GL if it satisfies all of the following. The first condition is the same as the notion of limit position. Gamma implies delta is not Gusai derivable in GL. However, second condition is slightly different. For any formula in Gusai, if this sequent is not Gusai derivable, then A is in gamma. And if this sequence is not Gusai derivable, then A is in delta. Note that the second condition does not require A to be an element of the union of gamma and delta, and this is somewhat different from the notion of the limit position. And the following lemma ensures that any Gusai underivable pair of sets of formulas can be extended to some Gusai analytically saturated pair. So lemma, let Gusai be a SF cross finite set of formulas and consider this set of formulas and suppose this sequence is not Gusai derivable. Then there exists a Gusai analytically saturated pair satisfying these conditions. And in the following, the set of all Gusai analytically saturated pair is denoted by W Gusai. So let's see how 2 points of improvement is overcome and how the open problem is solved. So first point, for any SF cross finite set Gusai of formulas, all of the following hold. The first one, the left rule for conjunction is Gusai admissible for any context, if and only if this condition holds, and this condition is truth condition for a conjunctive formula. And the second one says, the right rule for conjunction is Gusai admissible if this condition holds for any Gusai analytically saturated pair. And this condition is the false condition for conjunctive formula. And in both, the equivalence is claimed. So this is not only one direction, but also the equivalence is established here. So the first point of improvement is overcome. And the corresponding facts also for disjunction, classical negation, intuitionistic implication, and foursome. So we can overcome the first point of improvement. And let's see the second point of improvement. We successfully identify the semantic conditions for cut. So the rule cut is Gusai admissible if and only if this maximality condition holds for any Gusai analytically saturated pair. And the analytic cut is the equivalent to the restricted version of the maximality condition here. So we can identify the semantic conditions for cut. And the open problem is solved. We can get this theorem. Let Gusai be a SF cross finite set of formulas and suppose the semantic conditions for conjunction, disjunction, classical negation, and intuitionistic implication and foursome are satisfied. Then for any Gusai analytically saturated pair and any formula in Gusai, we can get this result. And this theorem ensures that the formula which is an element of gamma is regarded as true in the possible world, and the formula which is an element of delta is regarded as false in the possible world. So we can get the model for C plus J. So the open problem is solved here. And the summary of this section. 2 points of improvement of Lestow's analysis are overcome, and the open problem is solved. And the equivalence between the admissibility of the inference rule and the corresponding satisfaction relation for a complex formula is established. Thus, a tighter relation is provided. And the analysis presented in this section does not depend on cut and analytic cut. And moreover, the semantic conditions corresponding to cut and analytic cut are provided. And finally, the analysis presented in this section is carried out successfully for a combination of intuitionistic and classical logic. And this implies the open problem is solved. So let's proceed to the third part, and this is very short part. Debate between unilateralism and bilateralism exists, and unilateralism is a position claiming that only one linguistic act is primitive when the meaning of a formula or statement is considered. And the bilateralism is a position claiming that two linguistic acts are primitive when the meaning of a formula or statement is considered. And since analysis presented so far use the notion of assertion and denial, they are both based on bilateralism. However, I say that the unilateral approach is possible for C plus J. Because of the existence of classical negation, both of the Lestow's analysis and the analysis in the previous section for a formula in C plus J can be arranged based on unilateralism. And the transformation of sequent calculus to a one-sided calculus is the central idea. We can transform GC plus J to a one-sided calculus by using the following equivalence for any gamma and delta. This sequence is derivable if and only if this sequence is derivable. And the classical negation delta is defined as this. And note that this equivalence described above no longer holds if classical negation is replaced with intuitionistic negation. So I proceed to the summary of this section. I will talk only 1 minute, so I will stop. So by the transformation of sequence calculus, almost the same argument as in the previous section is possible. And since the calculus after the transformation is one-sided, the derivability of gamma represents the following situation. It is inconsistent to assert all the formulas in gamma. And the notion of denial is not used in this interpretation. And note that it is not guaranteed that this method based on unilateralism is also applicable to other combinations of intuitionistic and classical propositional logic. And finally, this is the final slide. I explain again about the contribution of this talk. A proof-theoretic analysis of meaning of a formula proposed by Greg Restow is improved by making use of the method provided by Takano. And the analysis improved by Takano's method is applicable not only to pure intuitionistic and classical propositional logic, but also to C+J, a combination of both logics. And finally, a proof-theoretic analysis of meaning of a formula in C+J can be obtained independent from the choice between unilateralism and bilateralism. Thank you very much for listening.
Okay, any questions or comments?
Much for your great talk. So I am really impressed with your technical soundness of your talk. So it is a very good result, I think. I would like to point out that not so essential point on philosophical interpretation of your result. Would you go back the difference between the bilateralism? Yes. Yes. So you said that since you have the classical negation, so we can interpret the Restow's situation of positions from the lateralistic way. So yeah, we don't have to take the bilateralism interpretation. Yeah, does my interpretation understanding is correct?
Yeah, but so yeah, when classical logicians try to understand the meaning of intuitionistic negation or something, they can use the classical negation so they can understand the intuitionistic negation in unilateral way, but not for intuitionistic logician, because intuitionistic logician does not presuppose the existence of classical negation. So it depends on the position. It depends on the position of the logicians, I think.
So thank you very much. I do think that the point is so it focuses on the very strange and understandable feature of classical negation. Mm-hmm. So you know, the classical negation is really strange relation. So if we can understand we can interpret the propositions in classical logic from monolateral way. So it just shows that the classical negation is really ununderstandable ununderstandable phenomena from the intuitionistic viewpoints. If we have some very strange thing, classical negation, then we can understand the classical proposition from intuitionistic viewpoint. So this just shows that I think we don't have to, we have not to say that we can take the monolateralistic viewpoint, but to say the classical negation is really understandable from intuitionist viewpoint.
But you are saying, I think you are saying is correct, but why you should choose the intuitionistic viewpoint? So from an intuitionistic viewpoint, bilateralism is good, and unilateralism is somewhat awkward because classical negation plays such a role, as you said. But why you should choose the intuitionistic viewpoints?
I understand what you want to say. Of course, I have just a very weak opinion that we can choose such a viewpoint. So that we can take the intuitionistic viewpoint, but it's possible. Yeah, but of course, from the more standard viewpoint, so what you are saying is sounds right. I agree on that.
So what is the question? So sorry. So
it sounds a bit strange that if we have the classical negation, so we can take the monolateral viewpoints. Sounds a bit strange. So it's my comment here.
Yeah. So So but when you say strange, you are in intuitionistic viewpoint, or you are not introducing that viewpoint, or?
So that's a big difficult question.
Okay. Yeah. Thank you very much for very helpful comment.
Thank you very much.
Yeah.
Thank you for a very interesting talk. I have two questions. One is short. Is your method applicable to predicate logic or higher order logics?
That's good. So for predicate, this procedure is essentially the this procedure is essentially the proof of the semantic completeness, Henkin type semantic completeness. So we can apply it to the first order logic, but we cannot use the method of Gusai because finite model property does not apply to the first order predicate logic. So we can get the infinite model, but so the core part can be applied, but we cannot restrict the model to the finite model.
Okay. So there needs to be some improvement.
Yes.
Okay. Thank you. And the second question is a bit more detailed. What you're doing is a proof-theoretic explanation of the meaning of logical constants, right?
Yeah.
But how is it related to the traditional proof-theoretic semantics by Dammit or Pravitz or Schroeder?
Yeah, that's a great question. So I think there are they are both inferentialist approach to logics or logical constants. So this is a common ground, as you know, maybe. But there are two differences, I think. The first difference is in proof-theoretic semantics, the meaning of the logical constant is purely syntactical object, right? Argument or proof or something. But this analysis uses the notion of a model after. This analysis introduces a notion of model even if we start from inference rules or arguments. So this is the first difference. And the second difference is this analysis does not imply which logic is good logic or right logic, but the proof-theoretic semantics defines the notion of proof-theoretic validity first. And in terms of proof-theoretic validity, they say which logic is good or which logic is right or something.
That's right. Okay, that that makes my understanding clear. Thank you very much.
Yeah.
Okay, so this is just a short comment. I think your result is related to the philosopher Timothy Williamson. So he argued that the combination of combining classical and intuitionistic negation is impossible. So he shows some kind of collapsing result in the old paper. And
So
do you know that?
it's a comment or?
It's just comments. So.
Oh, yeah. Thank you very much for, yeah. I think Timothy Williamson is very related to this, and I agree with the opinion. Thank you very much.
So let's speak again.